Vaporization. We've been talking about intermolecular forces, and these have an effect on vaporization. The molecules in liquid water are in constant motion. And so, we look at this static picture and they just look like they're sitting around. But I don't know who, but someone described this as a wild dance floor. So think of a mosh pit or something. And they're gyrating and moving around, and it's just like frenetic motion in that liquid. And so what happens if you have this beaker of water and you've got these guys moving around, if you get a water molecule moving toward the surface that has enough energy, it can break loose from the intermolecular forces that are holding them together. What are those forces that are holding water together? Dispersion forces, dipole-dipole, and hydrogen bonds. So those are holding the water molecules together, and those are strong. The hydrogen bonds are strong intermolecular forces, and so the water is going to be held together quite well. But there's an average kinetic energy for the molecules in water that is related to the temperature, but it's an average. And in that average kinetic energy, which is related to velocity, you have some that are at a higher temperature, a higher kinetic energy, and some that are lower. So if you get one that has a higher kinetic energy and is headed in the right direction, it can escape into the gas phase. So the way I think about this is a childhood game called Red Rover. Do you guys know what Red Rover is? I don't think they let them play that at school anymore because it's too violent. Someone might get hurt. But if you don't know, the way you play Red Rover is you line up in two teams, and that in itself is a problem these days. But the children hold hands in two lines with a big space in between, and then someone on one side says, Red Rover, send Sally right over. And Sally comes from her line, and she runs across, and she's trying to break through your hands, right? So you can imagine how children can get hurt. So the Red Rover line is the water molecules at the surface of the water. And the intermolecular forces are the strength of their hands holding each other. Some Red Rover lines are harder to break through than others. If you've got kindergartners playing Red Rover, or if you've got the O-line of the Fresno City College football team playing Red Rover, there's going to be a difference in whether you're going to make it through or not. So here's the Red Rover line, and these guys are trying to break through. They're running at it. They're only going to break through if they have enough energy to break through the line. So most of them are not going to get through. Just the more energetic ones are going to break through. When these water molecules get into the gas state, they do what gases do, and they go in a straight line until they run into something. If they happen to come back down and run into the water, they're going to get trapped again. So vaporization is the transition from liquid to gas. Condensation is the opposite, from a gas to a liquid. When the beaker is open, a lot of those molecules that make it into the gas state are going to escape. If it's closed, they're going to have the lid to bounce off of, and more of them are going to condense and get trapped again. So the average kinetic energy of a liquid is going to increase with temperature. The average kinetic energy of anything increases with temperature. And we've got some with, you're going to get kind of a bell curve like this. So here, blue at the lower temperature, and this is the minimum energy needed to escape. So you have to run at least that fast to break through the line. And so you've got a few that can break through. When you heat it up, you increase the average kinetic energy, you're going to get more particles that have enough energy to break through. So at a higher temperature, the water will evaporate faster. Does that fit with your observations from your everyday life of water evaporating? Yeah. If you have a wet washcloth and you stick it in the refrigerator, and an identical wet washcloth and you stick it out on the driveway in July, which one's going to get dry faster? The one on the driveway. The one on the driveway might be dry before you even get back in the front door. Higher temperature, the more particles have enough energy to escape from the liquid. Another way you can increase the rate of vaporization is to increase the surface area. At the surface, the molecules are held less tightly because they don't have as many neighbor-neighbor interactions. What makes more sense to me than that is that in order for a molecule to evaporate, it has to get to the surface. Right? Let's draw some pictures. Oh, sure, red pictures. There's no place. At the bottom. So if you think about that's not good. If you think about a tall, skinny container, and here's your surface area, or a shallow container, and here's your surface area. In this container, think about molecules of water in this wild dance floor, and not as many of them will be going in the right direction and come to the surface as in this one, where you have a much larger surface area. Here, there are just going to be more molecules running at the surface, and so more will be able to get through. That's how I remember that. To increase the surface area, you increase the rate of vaporization. And this makes sense too, because like if you take a glass of water, and let's say you take 2 glasses of water, and you leave one on the counter, and the other one you spill on the floor. Same volume of water, same temperature, but the one on the floor has a much larger surface area because it's going to spread out. The one on the floor is going to evaporate faster than the one in the glass, isn't it? Same temperature. What's different? The only thing different is the surface area. The strength of the intermolecular forces is going to affect the rate of evaporation. Because if the red rover line is very weak because it's kindergartners, you don't have to be going as fast to break through, right? A reasonably large adult could probably just walk through the line, right? And they're just not that strong. So at a lower temperature then, back up. With weak intermolecular forces, more of the particles are going to have enough energy. Let's go back to this graph. Oh, there it was. So what happens when you go to weaker intermolecular forces is that you've moved the line over here. You've moved the amount of kinetic energy needed to escape from here to here. And now there are a lot more that have enough energy to escape. And so the liquid will evaporate much more quickly. So we have 2 terms that we apply to liquids, volatile and non-volatile. A volatile liquid vaporizes easily, non-volatile does not vaporize easily. These are qualitative terms, not quantitative. But you know that some things evaporate quickly, like if you rub alcohol on your skin, it evaporates very, very quickly. If you rub vegetable oil on your skin, it's like never going to evaporate, right? Vegetable oil is very non-volatile. So of course we can talk about energy. There's energy involved in this. So let's think about that beaker again. And the beaker is insulated thermally. And so let's think about what happens to the temperature of the water as those molecules escape. The molecules that are evaporating are the faster moving ones, the ones with higher energy, right? They're the ones that have enough energy to escape. So the high energy molecules are leaving, what's left? The low energy molecules. So if all the high ones leave, what happens to the average kinetic energy of the water? It goes down. That means that the temperature drops. So as water evaporates, the water itself gets cooler. Vaporization is an endothermic process. We live in a very hot climate here in the summer, but it's also generally quite dry, which is nice. So you go outside and you get sweaty and a breeze comes and it feels cool because the sweat is evaporating off your skin. The particles that evaporate are the ones with the highest kinetic energy, leaving behind lower kinetic energy ones, which are going to then absorb energy from your skin. And so sweating cools your body. Where I grew up in Minnesota, it just doesn't work as well. If it's 90% humidity, sweating doesn't do much good. It just gets you really, really wet and smelly. So it's nice here that when you sweat, at least it does some good. North Carolina is like that too. So vaporization is endothermic. It requires energy to come in. Condensation is exothermic. Does it feel good to hold your hand right over the surface of boiling water? No, it will burn you. Steam can actually burn you much worse than boiling water can. What happens is that the steam, which is very high in energy, condenses to water on your skin, and where does all that energy go? Into your skin, causing a burn. This concept of condensation and vaporization and the related energy has an effect on weather. Here, where the humidity is relatively low, we commonly have large temperature variations. It's not at all uncommon to have the temperature swing 40, 50 degrees from night to day because there's very little moisture in the air. In places like Minnesota, the daily temperature variation might be only 10 degrees. So there's so much moisture in the air. What happens is as the temperature goes down, the water will start to condense. When the water from the air condenses to the liquid, it gives off energy, keeping the air warm. And then when the sun comes out and it evaporates, it absorbs energy, but it ends up moderating the temperature. Here, where there's very little moisture in the air, as soon as the sun goes down, the temperature usually falls dramatically. And like the last couple of weeks where it hasn't done that, the humidity has been higher. And it moderates the temperature by absorbing energy and releasing it and keeping the daytime highs and the nighttime lows roughly the same. And you see that if you go to the coast. Big body of water. There's evaporation and condensation going on, tremendous amounts of energy, and that moderates the temperature. Enough meteorology. So of course, we're going to do calculations about this. The heat, or more properly, the enthalpy of vaporization is just the amount of heat required to vaporize 1 mole of the liquid at its normal boiling point. And so to vaporize water from the liquid to the gas, you're going to have to put in 40.7 kilojoules per mole. This is always going to be a positive number because it has to go in. It's somewhat temperature dependent, that's why we say at the normal boiling point, but we're not going to mess around with that too much. So here at the normal boiling point, it's 40.7. At 25 degrees, it's 44. We can compare heats of vaporization for rubbing alcohol, acetone, and diethyl ether. So let's think about this for a minute. Diethyl ether is a fairly nonpolar substance, and it doesn't have any hydrogen-oxygen bonds. So this pretty much has dispersion forces, and water has hydrogen bonding. And look, there's a difference between the heat of vaporization. It requires a lot more energy to vaporize water than it does diethyl ether, because the intermolecular forces are much weaker for the diethyl ether. When the substance condenses, it's the same amount of energy involved. So the equation is backwards, and just like we learned when we were doing heats of reaction, we're just going to switch the sign on the heat of reaction here. So it's minus 40.7 is released when it condenses. So this allows us to convert between amount of energy and moles of substance vaporized or condensing. So let's calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. Let's just double check our number there. At the boiling point, 40.7, and the units are kilojoules per mole. So delta, oh, I didn't want red. Delta H of vaporization is 40.7 kilojoules per mole. So we're looking for the amount of heat in kilojoules to vaporize 2.58 kilograms of water. This gives us the relationship between kilojoules and moles. So what do we need to do? We need to take this mass and convert it into moles. And then we can use this as a conversion factor. So this ends up being dimensional analysis. We're going to take kilograms to grams to moles to kilojoules. So 2.58. Now I've done this kind of shortcut before, and I don't want to mess people up. Does it make sense to you when I convert this by putting what kilo means in there instead of kilo, or would you rather I just write the whole thing out?
No, it's good.
Is that good? Is everybody okay with that? So when we've got this prefix here, the fast way to convert is instead of kilo, I write what kilo means, which is times 10 to the third grams. So just to be clear, that is the kilo part. And sometimes that'll end up with your number not being in proper scientific notation. That's okay, because you're just going to put it in your calculator, and your calculator will understand. So now I've got grams. I need to convert to moles. So I want to multiply by moles and divide by grams. And then I want to multiply by kilojoules and divide by moles. So I made my path. It's my plan, and I'm going to follow it through, putting things in so the units work out. There's no equation to memorize. We're just going to convert units. What's the relationship between moles and grams for water? 18.02 grams of water per mole. That's the molar mass. 2 hydrogens plus an oxygen gives us 18.02. And then the relationship between kilojoules and moles is this guy right here, 40.7. And you would either be given that or you'd have to look it up. That's not something you can just figure out. And I wouldn't expect you to memorize that either. 2.58 times 10 to the third divided by 18.02 times 40.7. And my calculator is showing me 5827.192009. How many significant figures should I put? 3. So, right there. That's the tens place. We have to be careful. So we want to put this in scientific notation and then round it off. It's going to be 1, 2, 3. So it's going to end up being 5.83 times 10 to the third kilojoules. You don't want to round that off to 583 kilojoules. Any questions? Well, we looked at water in an open beaker. What if it's a closed container? So here we have water, wild dance floor, more energetic ones are breaking through the Red Rover line. Initially there was no water vapor, but gradually we'll get more and more escaping. Once we get some up here, then these guys are going to be bouncing around and some of them are going to run into the surface and condense and get trapped. So initially we only have evaporation. As evaporation, the amount that has evaporated increases, then the amount of the rate of condensation is going to increase. And what's going to happen is eventually we're going to get to a point where there's an equilibrium established, where the rate of evaporation is equal to the rate of condensation. The rate of the evaporation here is going to depend on the surface area of the water, and it's going to depend on the temperature of the water. And so the rate of evaporation is not really going to change. The rate of condensation is going to depend on the number of gas molecules that are present. The more gas molecules you have, the more will be hitting the surface and getting trapped. So it depends on the concentration or the partial pressure, because we don't usually talk about concentrations of gases, we talk about their pressures. So the more gas there is here, the higher the pressure of that gas is. And the higher the pressure, the faster it will condense. So here is rate as a function of time. So the rate of evaporation will be constant over time. The temperature is not changing, the surface area isn't changing, so the rate of evaporation will be constant. This this flask is not insulated, and so we're going to ignore any temperature change from the evaporation. The rate of condensation will start out at 0 because there was no water in the gas state to condense. And as more of it evaporates and the concentration or pressure of water increases, the rate of condensation will increase. And eventually we'll get to a point where those rates are equal. And this is called a dynamic equilibrium. Let's go back to this picture for a minute. If you took pictures of this where you could actually see the molecules, once it's reached dynamic equilibrium, if you took a picture like every 5 minutes, what you would see is that you have the same number of gas molecules, but they are not the same gas molecule because there's evaporation occurring and there's condensation occurring. It's a little bit like at a busy airport. The number of people in the airport may be relatively constant, but you have planes coming in and you have planes going out, and so it's different people. It's not the same people. So that's how it is here. We've got the same number of gas particles, but they're not the same gas particles. This is not something that's static and everything's just, oh, we're not doing anything. It's constant evaporation and condensation at the same time. What we call the vapor pressure, we've talked about the vapor pressure of water. The vapor pressure is the pressure of a gas in dynamic equilibrium with its liquid. So in that flask here, when equilibrium has been established, these water particles are exerting a partial pressure, and that's called the vapor pressure. The vapor pressure is going to depend on the intermolecular forces, because if the intermolecular forces of that liquid are weak, how does that affect the rate of evaporation? Weak forces, faster evaporation, right? So if the rate of evaporation is greater, then when we get to equilibrium, we're going to have more gas particles, and so the pressure will be higher. If the intermolecular forces are very strong, you'll have fewer particles in the gas state and a low vapor pressure. Let's see, do they do that next? Can't press that button. There's one more thing I want to mention. The vapor pressure depends on the temperature. So if we go back to this guy again. The rate of evaporation depends on the temperature. So if you increase the temperature, you increase the rate of vaporization, you're going to increase the number of gas molecules that are present at equilibrium. And that's why when we used Dalton's law of partial pressures and collected gas over water and subtracted things out, when we looked it up in a table, the vapor pressure of water changes with the temperature. At higher temperatures, it's a higher pressure, and at lower temperatures, it's a lower pressure. When we have a dynamic equilibrium, Le Chatelier's principle says that it will respond to a disturbance in an attempt to restore its state of equilibrium. So basically you can think of it as the equilibrium fights back against any changes you impose on it. So here we have an equilibrium between a liquid and its gas. If we increase the volume of this container, that causes the pressure here to decrease. That lowers the rate of condensation. The rate of evaporation remains the same, and so we're going to get more gas particles to come up here and reestablish that dynamic equilibrium. If we compress it, then we're going to increase the rate of condensation because there's more pressure of gas. There are more gas particles in a smaller area to condense, and then that will cause the pressure to go down. So if you increase the pressure, the equilibrium changes to lower the pressure. If you lower the pressure, the equilibrium shifts to increase the pressure. It's trying to stay the same. Temperature dependence. When the temperature increases, the vapor pressure increases. I got ahead of myself and already told you about that. We can have a small temperature change that results in a large change in vapor pressure. We see that these guys, diethyl ether, ethanol, and water, their vapor pressures are very strongly dependent on their temperature. Ethylene glycol, which is the in antifreeze, has a very low vapor pressure, and it is not as dependent on temperature as water is, which is one of the things that makes it useful as an antifreeze. The boiling point of a liquid is the temperature at which the vapor pressure of the liquid equals the atmospheric or external pressure. So if we go back to this graph right here, at 100 degrees Celsius, the vapor pressure of water is 760 millimeters of mercury, or 1 atmosphere. And we know that water boils at 100 degrees Celsius. What's happening here, and the reason we get these big bubbles forming, is that now pretty much all the molecules have enough energy to break loose, even the ones in the middle. And so they will actually form bubbles of gas within the liquid. Those, of course, have a lower density than the liquid around them, and so they'll rise up and escape that way. One of the things I remember from high school is that when we talked about this sort of thing, my crazy chemistry instructor had a giant vacuum flask, and he put some water in the bottom of it, and he had a big vacuum pump, and he started the vacuum pump, and he started lecturing. And after a while, the water in the flask began to boil. And then he made us all come up and touch it. And of course, the first person is afraid to touch this because boiling water is hot, right? You're going to make us put our hands on boiling water? But we touched it, and it was room temperature. Water was boiling at room temperature. It just messes with your mind. It really does. How could that happen? Well, he had it in a flask, and he was pumping air out of it, reducing the pressure. So at 25 degrees, if you get down to a low enough pressure, the water will boil at room temperature. A liquid boils when its vapor pressure equals the external pressure. The normal boiling point of a liquid is the temperature at which the vapor pressure equals 1 atmosphere. And so that's 100 degrees Celsius for water. We say normal boiling point because you can make it boil at various temperatures by messing with the pressure. So the normal boiling point is where you're not messing with the pressure. I don't want to do that yet. So, you know what a pressure cooker is? Anybody? Yeah? People use pressure cookers to cook food faster because you put a lid on and you clamp the lid on, and as the water heats up, it builds up pressure. When the pressure is higher, is the water going to boil at a lower or higher temperature when we increase the pressure? It's going to boil at a higher temperature. And so the water is hotter and it will cook your food faster. And that kind of ties into this. What happens as you heat water, the temperature goes up, and that makes sense. Once you get to the boiling point, the temperature doesn't change. It stays constant. So if you've got a pot of boiling water and it's been boiling for 5 seconds, or if it's been boiling for 5 minutes, the fact that it's been boiling longer does not mean that it's hotter. It's still 100 degrees Celsius. And I think some of you observed that when we did that molar mass of a volatile liquid. You're taking the temperature here, and it's like it's just staying at 99.7, and it's not going up, and I've been boiling it forever. Yeah, that's what's going to happen. It's going to flatten out. And so a heating curve for water is going to have a flat spot on it. And not just for water, for anything. So at this point, the temperature flattens out because all of the energy that is being put into that, the molecules are escaping and they're taking energy with them. And so you can't get any hotter until you've converted all of them from the liquid state to the gas state. So as long as there's liquid water present, it can't rise above the boiling point. And this is, there's a lot of correlations here with cooking. Sometimes when you cook something, you put water in the bottom of a pan, even when you bake it. And that moderates the temperature because it won't go above a certain temperature as long as the water is there. After the water's all vaporized, then the temperature will go up, and that's when your pot burns up. So the reason that a pressure cooker can cook your food faster is it raises the temperature at which the water boils, and at a higher temperature your food can cook faster. And that's why frying works faster too, is because oil can be heated hotter than water can. Another implication this has is at high elevations, the atmospheric pressure is less than 1 atmosphere, and thus water boils at a lower temperature, which affects cooking times. And so sometimes you'll see on a recipe or the box of cake mix, it will have high altitude directions. And that's because the chemistry of the cake is going to be affected by the different temperature that it will reach when you cook it. We're going to stop there.